Hello everyone, and welcome to today's webinar. I'm Don Kost, a technical marketing engineer for Siemens EDA. Today's webinar will focus on how Valor NPI can help you eliminate fab and assembly issues that you may encounter while working with advanced technologies. I'll start by looking at a survey that was done looking at different advanced technologies. Then we'll look at some of these technologies in more detail to understand how they are defined and how they are used. Finally, I'll have a short demo showing how Valor NPI can be used to find issues with these different technologies. So let's look at the survey results. Siemens recently conducted a survey among electronics OEMs in Europe and North America, detailing the technology and practices used by companies of all sizes. The study found that the use of these advanced technologies are, as we might suspect, heavily segmented across industries and geographies. Backdrilling and flex or rigid flex circuits are more common within the automotive companies. Controlled impedance is more common within communication companies. Controlled impedance is more common within Europe, while flex and rigid flex technologies are more common within the United States. And large enterprise companies are more likely to include nearly all of the advanced technologies surveyed: backdrilling, blind or buried vias, embedded active components, flex or rigid flex circuits, and HDI and microvias. One of the interesting results within the study was the use of advanced technologies by industry-leading companies. These leading companies showed that they were more likely to hit time, budget, and quality targets while still deploying advanced technologies a significant percentage more often. The data showed that these industry-leading companies are 24% more likely to use flex or rigid flex circuits, 46% more likely to use controlled impedance, 29% more likely to use embedded active components, 28% more likely to use embedded passive components, 50% more likely to use HDI and microvias, and 30% more likely to use backdrilling than any other technology companies within the industry. And despite having these technologies in place, they are still much more likely to hit their development targets. This is because they are also 32% more likely to use DFM software within their product design. So today, we're going to look at some of these technologies and how we can use Valor NPI to check to make sure that our product can be fabricated and assembled successfully. We'll start with HDI technologies. HDI stands for High Density Interconnect. HDI technology refers to the use of advanced manufacturing techniques to increase the number of connections, such as traces and vias, that can be made on a PCB, allowing for higher component density and more complex designs. HDI PCBs typically have finer lines and traces, microvias, and higher connection pad density compared to traditional PCBs. As electronic components and PCB real estate get smaller and smaller, microvias and HDI technology have become more viable solutions. HDI and microvias present many advantages for PCB design, such as miniaturization. These advancements in technologies enable the design of smaller and lighter electronics, making them suitable for applications where space is a premium, such as in smartphones or tablets and other portable gadgets. Signal integrity. The increased density of connections also enhances electrical performance and signal integrity in high-frequency applications. HDI helps in reducing signal distortion and electromagnetic interference, or EMI. Design flexibility. HDI provides greater design flexibility, allowing engineers to create complex multi-layer PCBs with intricate routing patterns. While HDI requires more advanced manufacturing processes, they can reduce overall PCB costs by enabling smaller board sizes. Because of the smaller copper features used in HDI, integrating a DFM strategy early in your design process will help you develop your design quicker and more cost effectively. One of the strengths of the Valor MPI software is that it can automatically identify HDI designs and then automatically enable the HDI checks. The Valor software interrogates the design before any analysis is run to look for the presence of certain factors. In the case of HDI analysis, Valor MPI will also automatically enable HDI checks if these two conditions are met. The design contains at least one microvia, and there is at least one buildup layer present in the stack-up. Once these conditions are met, the system will automatically enable the HDI checks without any user intervention. Valor has 53 dedicated HDI checks that are available. Here are the few of the checks that are available. Via pad to hole spacing. The removal of via pads to increase circuit density is common on HDI. Ensuring the distance from via pads to a neighboring via hole without pads is necessary when considering the manufacturing tolerances. Short line length. While trying to increase circuit density, often short segments of copper are generated. This can add additional burden to the etching process by creating obtuse angles in the copper. Non-orthogonal or non-45 line intersection. This check identifies connected lines intersecting at an angle other than 45 degrees or a multiple thereof. Lines in most cases should be aligned in multiples of 45 degrees to help with the etching process. This also helps with managing the impedance characteristics of the trace and to avoid other signal noise related issues. No core ground proximity. For HDI product models, the core layers are checked for a signal return path to minimize the circuit inductance by measuring the distance of the return path. This check reports signal vias lacking a corresponding ground via within the distance specified. This leads us to microvias. As stated earlier, microvias are needed to enable the HDI checks. HDI technology is directly tied to microvia usage. So what exactly is a microvia? The IPC now has a standard definition to help us with this. According to the IPC 6012 standard, a microvia has an aspect ratio of less than or equal to 1 and a drill span depth no greater than 9.84 mils. If these conditions are met, then Valor MPI will automatically enable microvia checking on a design. Along with the identification of a buildup layer, there is now no need to select the checks to run. The system will run them automatically. So let's take a quick look at the different types of microvias to get a better understanding of what types of checks are needed and why they are important. There are single microvias, staggered microvias, and stacked microvias. The IPC has also specified in IPC 2226 the different HDI structures that use these different microvia types. Type 1. This is the simplest of the microvia types. Type 1 contains a single microvia layer on either one or both sides of a core, and it uses both plated microvias and plated through holes for interconnection. Type 2. Type 2 are a bit more complicated, like Type 1 in the sense that they contain only one microvia layer on one or both sides of the core and use both plated through holes and plated microvias for interconnection. Unlike Type 1, this type uses both buried and blind vias. Type 3, the most complex. This type contains at least 2 layers of microvias, along with buried and through vias. To check all these different types, we need a robust DFM tool. Valor has 32 separate microvia checks available that can check all the different combinations of the above microvia types. Here are a couple of the microvia checks that are available. Valor MPI can check all 3 microvia types. Buildup to buildup. There are checks to look at microvias that are in buildup layers. Drilled holes on buildup layers that are too close to each other edge to edge compromise the structural integrity of the PCB. This can lead to the plated barrel of the hole cracking during production or product use. Core to core. There are checks to look at microvias located in cores that are too close to each other. Buildup to core. And there are checks to look for issues between buildup and core layers. Stack count. There is even checks to look at the depth of stacked microvias. The depth to which a microvia penetrates the layer stack-up can affect board yield. Stacking more than 3 microvias are more likely to experience failures than staggered microvias. Continuing with the advanced technologies, we'll look at rigid flex designs. A rigid flex PCB is composed of a combination of rigid boards and flexible circuits that are permanently laminated and interconnected to one another through vias. The benefits of a rigid flex PCB design include space efficiency, enhanced reliability, durability, weight reduction, improved signal integrity, design flexibility, and environmental resistance. These advantages make rigid flex PCBs a versatile choice for a wide range of applications across various industries. As with all good things, there are pitfalls that accompany the use of rigid flex designs. Some of the challenges of routing a rigid flex design are: routing traces parallel and vertical within a bend area. There are no vias allowed in a bend area. And distributing the conductors evenly on a layer. Routing wider traces near the edges. Offsetting traces on adjacent flex layers. Avoiding 90-degree trace angles. And also avoiding holes too close to an interface area between the flex and rigid sections. Valor has 79 flex and rigid checks available. These flex checks will automatically be enabled if the system detects flex subtypes of signal flex or power ground flex in the matrix. These subtypes can be seen using the matrix viewer. Here are just a couple of the rigid flex checks that are available. Holes too close to an interface area. Plated through holes that are too close to an interface area result in a plated hole very close to a rigid flex transition, which could lead to stress on the plated hole barrel, resulting in cracking. Line changing direction in a bend area. When a flexible portion of the board is bent, the copper lines in that area are subjected to either compression or tension, depending on the layer position relative to the bend. A change in copper line direction within the flex area would focus stress at the location of the change in direction, which leads to copper line fracture concerns. Overlapping lines in a flex section. Traces on adjacent layers in a flex region that overlap will likely generate what is called an I-beam effect. This condition will negatively impact the flexibility of the flex region. Stiffener too close to a bend area. A stiffener placed too close to the bend area places additional stresses on the flex materials in that area that may lead to material defects. To help visualize how the Analysis Definition Manager operates, here's a flow chart defining what factors are needed to trigger the software to enable HDI, microvia, and flex checks. First, it will look at all the layers of the design to determine if the flex analysis needs to run. There are several extra checks that are enabled during flex analysis, such as bend area analysis, as well as transition area analysis that are not needed for rigid-only designs. If there is at least one copper layer with the subtype of flex, then the rigid flex analysis will be performed. Up next is microvia analysis. Here the system will check for the presence of any microvias. Microvia analysis is performed only if at least one drill layer contains one or more rounded drills of non-zero diameter that meet the IPC standard definition for microvias. As stated before, the IPC definition says the aspect ratio is less than or equal to 1 and a depth less than or equal to 9.84 mils. That's the out-of-the-box definition, but it can be changed by your DFM SME to match your definition of a microvia. And the final system level factor check looks at an HDI stack-up. HDI analysis will be performed only if the design meets these two conditions I have previously stated. First, the design must have microvias, and secondly, the design must contain at least one of the copper layers that has a layer type of buildup associated with it. Once this evaluation is done, the system will now automatically run the correct checks. The next advanced technology we'll look at is backdrilling. Backdrilling is a technique used to remove the unused portion of the stub in a printed circuit board. This is removed by using a drill that has a diameter slightly larger than the diameter of the original plated through hole. In practice, it is achieved by redrilling the plated through hole to a predetermined stub length of less than 10 mils from the signal layer. Backdrilling is a critical technique in modern PCB design, particularly for high frequency and high speed applications where maintaining signal integrity and reducing EMI are paramount. It ensures that only necessary vias are connected to the signal paths and that any excess vias that could negatively impact the performance of the PCB are effectively removed or controlled. Valor has 16 backdrill checks. Here are a couple of the backdrill checks that are available. Backdrill to copper spacing. So the backdrill to copper spacing is the distance that must be maintained from the edge of the backdrill to the edge of all copper connections on layer penetrated by the backdrill. Backdrill to drill. Backdrill spacing is the distance that must be maintained from the backdrill to neighboring drills of different types. Backdrill smaller than plated drill. This reports backdrill locations on drill layers with the subtype backdrill where the backdrill diameter is smaller than the corresponding plated through hole. Such a condition would never result in effectively removing the plating in the hole, deeming the backdrill ineffective. Backdrill penetrates stop layer. This reports any backdrills that can accidentally pierce the stop layer and render the board unusable due to the signal trace being drilled out. The distance or the depth to the stop layer is the combined thickness of the copper and dielectric layers up to that layer based on the drill direction. And last, we'll look at the Valor Parts Library, or VPL. When using HDI with its increased circuit density, it's critical to make sure that there are no component interference issues. Having the ability to place an accurate package representation directly on top of the footprint in the design phase and not on the assembly line makes a huge difference in getting a product to market quickly. So what exactly is the Valor Parts Library? It's a library that we've been creating and maintaining for about 20 years now, following an ISO certified process. It's got over 2 billion manufacturing part numbers in it, and it's constantly being updated. The VPL library is basically parts that are drawn based on the data sheet, and our primary objective is to model the physical characteristics of the part, so it doesn't have any electrical characteristics, but it has one very important thing. It has the exact body and contact area of where the pin touches the pad. Right where the pin touches the pad is extremely important because what it allows you to do is solderability checks while still in the design stage of the product. So we start with the CAD footprint. Next, we bring in the corresponding Valor VPL library part. Now the solderability checks are performed. With these solderability checks, you know if there is enough heel fillet, toe fillet, left and right fillet. This is directly related to the reliability of the board, and that's something that is extremely important. So now that we have a better understanding of some of these advanced technologies, let's take a look at how we can use Valor MPI to locate these issues on a design. So now that we have had an opportunity to understand the different advanced technologies, let's look at issues that can be found using Valor MPI. The design I'll be using today is a rigid flex design with microvias. Because there are many webinars and videos showing the Valor MRA interface, I will be jumping right into looking at some of the results. I'll start by looking at some of the results related to HDI and microvias. The first check to look at is a microvia annular ring. As you see, it's broken down into top and bottom pads based on the drill span. This way you can have a larger pad, say on the top, to accommodate deep laser drilling where the hole generated is more of a cone shape than a cylinder. Here we are looking for an annular ring with a minimum value of 101 microns, but the measured value is 100 microns. Next, we'll look at an HDI layer check, via pad to plane. On HDI layers, it's critical to maintain the proper copper spacing between a copper area and the via pad on a buildup layer. Here we are looking for a 20 micron gap, but the measured value is 12.5 microns. Another HDI check looks at a short line angles that are multiples of 45 degrees. In this example, we have a line angle of 90 degrees. Having angles of 90 degrees can lead to etching issues such as acid traps. These angles can also affect impedance result as well as EMI signatures. Switching to the mechanical category, here we are looking at the spacing between two microvias on buildup layers. One drill starts on this layer and one drill stops on this layer. The constraint is set for a minimum spacing of 225 microns, and the measured value is 222 microns. The next check we'll look at is a core via overlap. This is a serious manufacturing issue since both holes cannot coexist in the same location. This check looks to make sure that a microvia does not overlap with a core or a through via. As we see, there is a layer 4 to layer 5 microvia overlapping a layer 1 to layer 14 through via. The last microvia check we'll look at today is one called microvia stack depth. This check reports a summary of the stack depths. I have the constraint set to look for depths greater than 2. The depth to which a microvia penetrates the layer stack up can affect board yield. The greater the number of layers penetrated, the more prone the microvia is to hole fracture. Here we see that there is a microvia stack depth of 3, which is a violation. Next we'll look at some of the rigid flex checks. We'll start with a few of the more important checks. If there are bend areas in your design, they will be brought over into Valor. Here we can see that the bend area is in green. It's important for long-term reliability that traces are perpendicular and don't change direction in a bend area. The first check I'll look at is to see if there are any traces that are not perpendicular. Here we can see that there are traces that are not perpendicular, and this would lead to fracturing of the copper traces. The next check looks for a direction change in a bend area. When a flexible portion of the board is bent, the copper lines in that area are subjected to either compression or tension, depending on the layer position relative to the bend. A change in copper line direction within the bend area would focus stress at that location of the change in direction, which leads to a copper line fracture concerns. It's also important to have the interface area between the rigid section and the flex section clear of solid copper planes. We can look for both outer and inner layers for copper too close to this interface area. The interface area is the dark blue here, and we can see that we have a copper plane on the outer layer that encroaches into the interface. The final rigid flex check we'll look at deals with copper traces that overlap in a flex region. This is commonly referred to as the I-beam effect. When traces on adjacent layers overlap, this can negatively impact the flexibility of the flex region as well as induce signal crosstalk. Here we can see that we have traces on layers 4 and 5 that overlap. Moving on to our next advanced technology, we'll look at backdrilling. The first check is looking for backdrills that are plated. To accomplish removing a signal stub, a backdrill must be non-plated. Having a plated backdrill is an error. The next check, back drill to drill annular ring, measures the difference in the plated drill size compared to the back drill size. It's important that the back drill is larger than the drill. The back drill to copper check looks at the size of the back drill to copper spacing. This is the distance that must be maintained from the edge of the back drill to the edge of all copper connections on the layers penetrated by the back drill. The final back drill check that we'll look at deals with the depth of the back drill. This reports back drills that can accidentally pierce the stop layer and render the board unusable due to the signal layer being removed. There is an overshoot value that can be set to make sure that there is plenty of margin from the depth of the back drill to the copper signal layer. Here, there is not enough margin to safely back drill this hole. And finally, we'll wrap up this demo with a quick look at some of the checks that can be performed when utilizing VPL. VPL allows you to check the package pins to the footprints on the design. Essentially, you're creating a digital twin of what you would see on the assembly floor. We'll start with a few solder validation checks. The first, through-hole pin gap, looks at the space between the hole wall and the pin. The recommended values called out by the IPC 2221 spec for this design would be 0.2 millimeters or 200 microns. As you can see, we have a measured value of 0, which means that the holes used for this footprint are undersized and that the part will not be able to be placed during assembly. Catching this now saves time and money. This next check is called quad pullback periphery. It looks at the center pad of a QFN part. We have a measured value of minus 300 microns, which means the pad of the CAD footprint is 300 microns smaller than the pin on the package. If you're asking yourself, how can this be? Let's look at the CAD package versus the VPL package. I'll turn on the pre-VPL component display, which will show us what the CAD package looks like. The white outline is what the package outline looks like coming from the CAD tool, while the light blue represents the VPL package. We can clearly see that the thermal pin in the middle is much larger than the footprint pad. If I turn on the top solder mask, we can see that I now have a solder mask defined pad, which is not optimal for the required heat transfer of this part. This part should be discussed with the librarian to address this issue. Sticking with this same part, we can also see that there is a problem with the toe distance of the pins. I am measuring the toe distance using IPC 7351 Level B spec. These soldering requirements can be set in the Analysis Definition Manager. Here we see that I should have a 300 micron toe, but the measured value is only 50 microns. Again, it's time to talk to the librarian, since this will surely cause issues during the reflow process. Since we now have the true packages in the design, we can also look at some of the component spacing issues. Here we are looking at a spacing issue between two BGA packages. We have a measured value of 0. Again, this will cause headaches during assembly. Let's quickly look again at what was used in the CAD tool to place these parts. Turning on the CAD package outlines, we can see that the outlines are about 1 millimeter apart. Unfortunately, we again need to consult the librarian about this part. So just having these couple of checks has saved an assembly line shutdown, since we can easily fix these issues before we send the data out. The last check we'll look at is another assembly-related check. Here we are looking for component leads that are shadowed by other components, rendering the AOI, or automatic optical inspection equipment, useless. In this example, the large inductor shadows the leads to the flat pack that is next to it. We are looking for a maximum angle between the parts to be 45 degrees, and our measure value is almost double that at 85 degrees. best practices would have us running these solder validation checks during the component placement stage of our design, where it's much easier to modify the placement. As we saw, using DFM in our design process is especially important when dealing with advanced technologies. Hitting your schedule, cost, and quality targets can be achieved with the use of a manufacturing-driven design practice. If you are considering the manufacturing aspects of your product early in the design process, Valor MPI can help assure that the product will meet all the critical requirements when manufactured. From the same survey, companies implementing manufacturing-driven design early in their process averaged 1.2 revisions per design with a cost savings of $20,000. I hope this webinar was useful, and I encourage you to take steps beyond DFM and consider implementing a manufacturing-driven design process. Thank you for taking the time to attend this webinar.